Good afternoon to everybody, and thanks for the kind invitation for presenting my research in this school. So today I'm going to talk about the use of plasmonic nanomaterials for driving chemical reaction, in particular for making hydrogen or use of plasmonic nanostructure in fuel cells. And probably most of you are, let's say, familiar with photocatalysis. So usually you have a semiconductor which absorbs light and creates electron and holes which have quite a high energy, and you can make a redox reaction. But in this presentation, I would like to show the potential of using a metallic nanostructure and what they do when you use them for driving chemical reaction. So probably most of you are familiar with plasmonic materials. For example, famous picture is the lithography. We can see the red color or the green color of the caps depends on the direction of the light which is incident to the cap, and this color is given by the nanoscale feature of metal nanoparticles. So usually, for example, most of you know that gold and silver are plasmonics. And for example, if you create like a solution or a colloidal solution of nanoscale particle, as you can see here, so the color is given by the plasmonic feature of the particle. So not only gold and silver are plasmonic particles, but any conductive material can be plasmonics. And so what's happened basically when a plasmonic or conducting material interact with light? So when we have nanoscale materials, basically they are able to concentrate light at nanoscale because the oscillation of the conducting electron at the surface match the frequency of light which is incoming on the material, and so basically we have like the coupling of the electromagnetic energy of light with the coupling of the electrons of the charge carrier oscillating at the surface of the material. And this creates quite interesting phenomena, especially if we think to chemistry, where we need electrons or holes to drive chemical reactions. So we can see that here, for example, typically an example of nanoparticles of silver or gold or copper exhibit like sharp absorption peak, which is due mainly by the size of the nanoparticle or the medium around the nanoparticle or the materials which is made the material itself. And we can see that usually we have a strong resonance or a resonance which is centered at a specific wavelength. But in the moment we organize this nanoscale metallic nanostructure on a surface, like in this case, we are able to create even more exciting opportunity. For example, creating ordered arrays of nanostructure. We can create the so-called metamaterials or metasurfaces, which can exhibit properties which are usually not exhibited by a single nanostructure or by any natural material. And these optical metasurfaces are very important. Nowadays in optical technology, we can think that many companies are already funded and running in the US, for example, for making meta lenses, so ultra thin lenses which can resemble the use of the bulk lens that nowadays we use, for example, in microscope or in cameras and so on. But we can basically build the thin films of 200, 300 nanometer that can have many functionalities. These also are important, for example, for LiDAR, so technology that can be used for cultural heritage imaging and so on and so forth. So this is just a quick view of what we can do with plasmonic materials. And to go more in the fundamentals of plasmonic materials, we can see that the fundamental property of a plasmonic material when start to absorb light is that it is able to concentrate light from the far field to the near field and the optical cross-section is much higher than the geometric cross-section. And this is happening only in the moment that we have nanoparticles with deeply subwavelength size. This excitation, basically, this excites the conducting electrons on the surface of the materials and create very highly intense electromagnetic fields, so the hotspots, which can be used for many things. For example, a very famous application is surface enhanced Raman spectroscopy, which use the highly intense electric fields on the surface of a rough plasmonic materials to enhance the signal for molecules that has to be detected. After, let's say, this first moment, basically we have the dephasing or dissipation of the surface plasmon, which create a non-thermal distribution of hot carriers, as you can see here. So we have highly energetic hot electrons and holes, which of course can be used for many different applications, and which survives for a lifetime on the order of picoseconds. Afterwards, of course, there is a thermal dissipation, so we can use this material for creating intense local heating, and also in this case we can think to very common and famous application like local heating for photothermal therapy. But at the same time, we can also think to all these effects like that I mentioned, that we can use them for driving photocatalytic reaction, and this is quite a relevant field that is growing in these years. We can think that the INAE award for energy transition this year has been awarded for to Alas group at Rice University for developing this kind of photocatalyst based on plasmonic materials. And we can see that all these effects can be used, for example, for driving, for coupling plasmonic materials with semiconductor, or directly to driving transformation of molecules of interest. Here you can see some articles and review from my group, and also some commentary which can be really readable from readership from many different backgrounds. And here I would like to summarize what we do in my group. Basically, in the current years of energy transition, what we are trying to do, and all the community of solar fuels is trying to do, is to develop technology like photocatalysis, electrocatalysis, and other technology to convert small molecule into fuels, like, for example, hydrogen or hydrocarbons or ammonia, etc. And basically using solar light or other renewable energy sources to make a more sustainable process, to basically replace the energy-intensive industrial chemical processes that usually are used in the industry. So what we use basically is our, let's say, fundamental postulate that we use surface plasmon for all this kind of technology, like photocatalysis, electrocatalysis, and solar thermal technology to drive chemical reaction. And this is possible because, as we've seen before, with surface plasmon, we can manipulate all the fundamental process happening during catalysis or photocatalysis. So we can manipulate light absorption, charge separation, and lifetime of these charges. We can manipulate surface catalysis, so speed up some reaction or not. And also we can manipulate how the molecule absorb or desorb on the surface. So we can induce, for example, light-induced desorption of some molecules that sometimes poison the catalyst surface. So we can regenerate catalysts with this kind of materials. And in particular, I would like to discuss more about the possibility that we can have with plasmonic materials. In particular, as we have seen, we are able to generate highly energetic carriers, or we can also generate at the same time intense local heating. So it's important then to determine how the chemical reaction under study basically speed up. So is a thermal effect or non-thermal effect due to the hot carriers that we produce. And this is quite important because, for example, if we take, we consider like how chemical reactions proceed. Usually you have like ground state potential energy surface. From your reagent A, you have to go to the product B. You have basically a potential barrier. What happens usually in the thermal-driven processes like the industrial one, basically you provide enough thermal energy to overcome the energy transition barrier and to go to allow the products to reorganize, go to the intermediates, and then go to the product. When you use instead light-induced photoexcited carriers, basically you can jump on the an excited potential energy surface, and you can have a different reaction mechanism. Basically, you can change or manipulate the selectivity. You can change, for example, having different products or more selective formation of one product rather than another one using the photoexcited carriers. And this, of course, is very important because the improvement of selectivity during catalysis is something that can bring many benefits on the economic point of view of an industrial process. On another note, indeed, also it's very important to determine the temperature that you generate in the system, because of course the reaction rate of a reaction depends through the Arrhenius equation on the temperature that is generated. So understanding then the condition generated in situ during the light irradiation is very important to determine whether we're driving the reaction using only photoexcited carriers or only increase of temperature or both the effects. And it's interesting also, of course, having the possibility to use both effects, so we can speed up reaction generated in situ high temperature, and then maybe with a energetic carrier we can modulate the reactivity and the productivity of our catalysts. And here I would like to show just one example of this case. In this case, we use plasmonic nanocubes made by titanium nitride, which is like an alternative plasmonic materials with similar properties like gold. You can see the absorption spectra basically is centered around 600, 700 nanometer. So the appearance of titanium nitride is similar to gold. Indeed, if you think, for example, to drill bits or many roof of Orthodox churches, they look like golden, but they are not covered by gold. Usually they are covered by titanium nitride thin films. And so in the same way, we can study nanoscale titanium nitride for catalysis by trying to substitute gold nanoparticles, for instance. Of course, titanium nitride is much more, is cheaper, is like abundant, and also importantly, is a refractory materials. So as a melting point around 3000 degrees centigrade. So it can be very interesting for using in extreme condition. Also, titanium nitride is very resistant to acid. And in this case, as I mentioned a few moments ago, we use like nanocubes of titanium nitride decorated with platinum nanoparticle for hydrogen evolution. In particular, we use it for the dehydrogenation of ammonium borane, which is a chemical of interest to be used as a hydrogen storage materials. As you can see here, many materials can evolve hydrogen from ammonium borane, but using Glide we can have much increased rates of hydrogen evolution. Here you can see the absorption of the light in these composite nanomaterials. You can see that most of the absorption is within the titanium nitride structure, and a small percentage of the absorption is within the platinum nanoparticles. But also interesting features which happen when you couple, for example, a non-plasmonic material like platinum to a plasmonic material like titanium nitride. You can see from the spectra on the right hand side of the slide, the absorption of the platinum can be resonantly enhanced by the plasmons. if you compare this with the absorption of isolated platinum nanoparticles. This also brings interesting effects, so meaning that we can have different mechanisms of hot carriers production. So we can have, for instance, the formation of electron holes titanium nitride, which then can be transferred to platinum where the reaction occurs, or you also can generate directly the hot electrons into the platinum. So this also can bring some increase in efficiency. Here you can see some feature of our reactions. So the first thing that I would like to highlight, for example, we see and concentrate the apparent quantum yield plot on the left-hand side of this slide. You can see that we have like an apparent quantum yield which is above 100%. So this is maybe, if you are familiar with photocatalysis, can be quite strange result. Usually when you use semiconductor, you can have maximum 100% of quantum yield, because with one photon you generate one electron and one hole. However, so there are some materials which can already semiconductor which can produce more than one carriers per photons. And in the case of plasmonic materials, actually, we have to remember that with one photon we excite a collective motion of electrons. So meaning that we have many carriers which are excited and produced at the same time when the photon strikes the materials. There are also reports, for example, in the literature with 700 or 800% of quantum yield. So this it's quite an interesting effect of these materials. And as you can see here from the plot on the right-hand side, if we use solar light with different intensity from 1 sun to 10 sun, we are able to basically increase of 1 order of magnitude the rate of hydrogen evolution, passing from the dark condition to the 10 sun under photothermal condition. The red plots, as you can see here, are quite lower in intensity in comparison with the blue ones. And basically, the red plots represent the reaction rates measured in the dark at the final temperature generated under light excitation. So this basically brings the measure on how much the reaction under light condition is driven by only temperature. So we have like basically a half of the rates is given by the increase in temperature in the catalyst, and the other half is given by the production of non-thermal excited hot carriers within the materials. And we also did some kinetic isotopic effect to going more into the mechanism, and what we discovered is that basically under this condition, under light condition, we are able to decrease the energy of the transition state by almost by half of the initial energy under dark conditions. And so basically what we think is happening is that the hot carriers which we produce on the platinum surface are able to speed up the rate determining step, which is the rupture of the water molecules to start the hydrogen evolution with the monoborane molecules. And overall, so this was to show that basically using this strategy, we can enhance by 1 order of magnitude the activity of one catalyst, metallic catalyst, in respect with the dark conditions. And for example, this can be interesting if we think that if we substitute, for example, platinum with non-noble metals, and using this kind of strategy, we could bring the activity of non-noble metals to the one of noble metals. So this, of course, has implication in the use of technological implication, the use of fuel cell and other technology for hydrogen generation. This is from this example of using metal nanoparticles. Now I want just to focus more on the use of metal surfaces. So as we saw before, basically when we have metal nanoparticles like isolated particles, metallic nanoparticles, we have like a localized surface plasma resonance, which has like an absorption a band which depends on the size of the particles, on the medium and the material which compose the particles. Then basically, if you want to use like different region of the solar spectrum, you have to change the shape, change the size of the particles, and so on and so forth. But the one you put organized like periodically these particles on a surface, then you obtain something which is like called metasurfaces, which can have like the property or optical property which you desire. For example, we can design and realize films on the order of 200 nanometers in thickness, which absorb all the solar spectrum, covering all the solar range. Or we can have, for example, different resonances, like very sharp resonances, meaning that we will have very intense and highly intense electric fields on the desired wavelength. And so we can do basically different things, and we can design the materials depending on the functionality we want to achieve in the final device. And what is interesting, for example, you would say, okay, I can achieve 100% of solar absorption in the solar range using this kind of material, but I can do the same, for example, using carbon black nanoparticles or silicon-based paints, which are already commercial and very cheap. This is true, but as you can see here, basically the game-changing in using plasmonic metasurface and in general optical metasurfaces, that we can use much thinner films to achieve the same absorption, meaning that we can miniaturize devices, we can do lightweight devices, and we can focus on using really ultra thin films for making new smart devices. Here, from a fundamental point of view, you can see on the right-hand side, for example, a metasurface based on the arrangement of titanium nitride nanocavities or nanocylinders. And you can see here, basically, that the absorption of light is completed under the first 200 nanometer of thickness. So this, of course, is quite incredible and unique for the plasmonic metasurfaces properties. On the other side, from the point of view of generating carriers and making photocatalysis, here we can see that depending on the shape of the meta atom, so the single unit which creates then all the metasurfaces, we can have different resonances basically, or different efficiency in generating the out carriers. We can see here, for example, that comparing a cavity, a sphere, a cube, or a disk in contact with titanium oxide, basically we can inject much more electrons and use holes for photocatalysis, for example, when we use a cube instead of the other shapes. So we have like many different degrees of freedom to manipulate light and also chemical reaction as a consequence. And here some example of how we use the metasurfaces for catalysis. In this case, these are two examples of use of plasmonic metasurfaces for photoelectrochemical water splitting cells. In this case, we use these devices as photoanodes, so for the oxidation reaction. As you can see in the first case, basically, we sandwich like a semiconductor used for this kind of application like hematite between a gap plasmon structure, meaning we are able to squeeze light between a mirror made by gold and small nanostructure on the top of the hematite field. And this geometry, as you can see here, can bring like a doubling of the photocurrent if we compare, for example, with the planar hematite film. The mechanism behind this, basically, you can see that from the high PCE, so the incident to photocurrent efficiency, so the wavelength, the action spectra, basically here we measure the photocurrent at each wavelength, and then we record the photocurrent basically and calculate the efficiency. You can see that the highest increase is before 600 nanometer, meaning within the band gap of the hematite. We have also a small contribution in the enhancement at longer wavelength, as you can see here, which is due to the localized surface plasma resonance and gap plasma resonance of the structure. And in particular, the mechanism is due to the hot carrier injection. But the highest effect is the scattering or light trapping effect created within the hematite and exciting the electron holes generated by the interbed transition in the hematite. And a similar effect is that happen also in this second example. In this case, we create a self-standing photoanode made by nickel nanopillars and covered with platinum to infer more robustness in terms of chemical stability, and a cadmium sulfide semiconductor which drives the oxidation. And also in this case, as you can see, we can obtain broadband absorption and a very high increase in photocurrent. We can triple the photocurrent if we compare the planar films in comparison with the one made by the nanopillars. Now, in this case, we have seen how plasmonic metasurface can enhance the activity of semiconductor used for photoelectrochemical water splitting. While in this second case, we will see how metallic metasurface basically can drive directly chemical reaction. In particular, in this example, we use this basically light enhanced anode for plasmonic direct methanol fuel cells to demonstrate this effect. What we did is to use always the same self-standing nickel pillars arrays and films, which is on the order of centimeter scale, covered with gold to enhance the optical properties, like ultra-thin layer of gold made by 10 to 30 nanometer of gold. And then with photo deposition, we use the electromagnetic hotspots to photochemically deposit the platinum nanoparticle, which are the catalysts for methanol oxidation, selectively only on the electromagnetic hotspots. As you can see here, and also in the SEM image, we don't deposit the catalyst on the flat surface, but mostly and mainly on the where the electromagnetic fields are higher. And this, of course, is important because what we want to do is to increase as much as we can the light-induced activity. So if we put like catalyst only where the light is concentrated, then of course we can maximize the functionality of the plasmonic metasurface. And here you can see that we can achieve different effects, different resonances of the nickel gold pillars. We can have broadband absorption due to cavity modes or hybrid cavity SPP modes, or we can have also hybrid resonances, which are due to the surface lattice resonance, basically where the diffractive modes of the nickel couple with the localized surface plasma resonance of each individual pillar, and so we can achieve these sharp resonances. The activity of these materials, I think, not working anymore. So here is the characterization in the methanol fuel cell of these materials. We can see in dark the activity of the materials, and when we shine the light with the solar irradiation, we can strongly enhance the response of the self-standing film. And as you can see, for example, from this picture, we can see that the temperature, if we monitor, for example, the potential at the peak of oxidation, we can see that changing only the temperature in the reaction medium basically doesn't change the peak position and the peak potential position of the in the cyclic voltammetry curve, but in the presence of light, you can see that you have a shift, a monotonic shift this peak, and so this is basically an indication that we are driving with the hot carriers reactions. And importantly, we can see that if we do wavelength dependent activity of our materials, we can enhance in a broadband manner the activity of these fields, and the mechanism depends on the energy of the photons. So basically, we can have, for example, the interband diodes of the gold mainly working in the mechanism to enhance the oxidation when we use more energetic photons, or we can have only near fields mainly enhancing the reaction pathway when we use near infrared light. And another example of fuel cell, in this case, we create a different metasurface. We use a nickel gold metasurface where we deposit palladium particles in two different ways using two different solutions, and we create basically two different nanoparticles deposited selectively on the pillars or not selectively over all the surface. And in this case, we use for fuel cells based on formic acid, basically oxidizing formic acid. We can basically generate hydrogen, and also, of course, drive the oxidation reaction in the fuel cell. As you can
Professor
see,
Naldoni?
Yes?
I'm so sorry, but the time closed, and if you can go to the conclusion.
Okay.
Thank you so much.
Yes, sorry to be long. No. So I will just show here like possibility to do also solar thermal catalysis using these materials, so we can achieve, for example, 600 degrees centigrade and use this for CO2 reduction or CO oxidation instead of using thermal reaction. So to summarize, basically, I've shown half of the possibility that is that are able to be done with plasmonic materials for solar to chemical energy conversion. And we have seen that with either with plasmonic nanoparticles or metasurfaces, we can use unusual optical phenomena to drive in a different and more efficient way chemical reaction.